Hello and welcome to Azure Cosmos DB Conference 2023. My name is Parag Avadia and I'm a senior software engineer at Adobe. Today's topic of discussion is how we used Azure Cosmos DB to power Adobe Experience Platform's Datagroups. Before we move along into the presentation, I would like to discuss a few keywords that will be used throughout these presentation. First of all, Adobe Experience Platform. Adobe Experience Platform is a data platform used by digital marketers to ingest big data and then create digital marketing actions such as email campaigns and digital marketing ads. The Adobe Experience Platform is powered by Azure Data Lake, and at the center of Adobe Experience Platform is an object called as datasets. The dataset object stores the metadata of the data on the data lake, such as the scheme of the data, location of the data, and the credentials of the data. Users use the metadata in dataset to read and write data on the data lake. Another important component that we are going to talk about is the platform query service. The platform query service is a BigQuery implementation and allows users to read data from data lake using a SQL-like syntax. It allows users to join multiple datasets using query language. Now, we were asked to build a feature called as Datagroups to support reporting and dashboarding feature within AEP. A dashboard can have multiple report panels, and each report panel will use a query through platform query service to fetch the data from data lake. And you can imagine each report panel to be abstracted in an object called as data group. Let's dive deep into the product requirements for data group. As mentioned earlier, the data groups are used to power reporting and dashboarding. A data group has a collection of datasets, and it can also have a list of child data groups. And it's also important to know that a dataset can belong to multiple data groups to power different report panels. However, a data group cannot have only one parent. The data group metadata should be exposed through a REST API to perform list and CRUD operations. During the read operation, the data group metadata returned through the response payload must contain its immediate parent and children. If you look at the graph here, you can see a data group can have multiple data group children, multiple dataset children. A dataset can belong to multiple data groups. So this looks more like a graph data structure. As a result, we had some engineering concerns as we were parsing these requirements. One of the concerns that we had was that the dataset object already existed and was supported through a different service. And we cannot change the service because it will disrupt existing user workflows. As a result, we made a design choice to store dataset references in data groups. This presented a very unique problem. As you saw earlier, a dataset can belong to multiple data groups. As a result, when a dataset is deleted, we need to perform multiple updates to remove all of these references from data groups. And this operation should be atomic, which means that we cannot be in a state where dataset reference has been removed from some data groups and it still exists in some data groups while it has been deleted. Another important aspect is that, as we discussed earlier, it is a graph data structure, and graph data structure presents its own unique challenges. In graph data structure, you're almost always guaranteed to run into graph traversal scenarios, which can be very complex. Another problem that graph data structure present is that it can result in complicated user experience. For instance, if a user is expanding upon a data group, we don't want a scenario where they are in an endless loop of just traversing through a data group within a data group, or their page just has thousand or even hundreds of thousands of data groups. Such data structure is unnavigable and results in poor user experience. Also, in such scenarios, we can also run into performance issues if we try and load a large number of data groups. As a result, we were required to implement guardrails to ensure both good user experience and consistent performance. We started looking into what kind of database will best support our requirements. Intuitively, we looked into document databases, which we were using to power other services within AEP. Most document databases, if you go by CAP theorem, are partition fault tolerant and highly available. However, they are eventually consistent. As a result, they scale horizontally. Most document databases store data in JSON format, which provides flexibility and extensibility and allows the data to grow organically as the time progresses. Most document databases support indexes, which is very helpful for the scenario where a partition may have large number of documents, but the query can still be performant as it is using the indexes. The document databases are excellent to support search and sorting operation because they provide a robust querying mechanism. However, the downside of using document databases is that, at least at that point of time, they didn't support transactions. If you recall from the scenario of dataset delete where we wanted to update multiple data group preferences, this was a key requirement for us, but it was not supported by document databases. Another issue we ran into with document databases was that some document databases had a querying mechanism to traverse hierarchical data structure, but it was not robust enough to provide predictability to ensure query performance. And as a result, guardrails were very difficult to implement using that query language. Next, we started looking into traditional graph databases since the underlying data structure is a graph data structure. Just like document databases, the graph data structures are partition fault tolerant and highly available, although eventually consistent. As a result, they ensure horizontal scalability and high availability. The graph databases have native support for graph traversal through its query language, which is very helpful for the scenarios that we talked earlier. The graph databases often allow different kind of objects to be stored, and then it provides a mechanism to discover relationship between these different type of business objects. However, the graph databases are not very good when it comes to powering traditional search and sorting operation. The data model is not quite intuitive, and as a result, it requires quite a learning curve for developers to figure out how the data should be stored and queried. Then we started to look into Azure Cosmos DB, and some of its features were very impressive that got our attention. Just like document databases, Azure Cosmos DB is eventually consistent, but it is partition fault tolerant and highly available. So by CAP theorem, it should allow horizontal scalability and high availability of our service, which is excellent. The unique aspect about Azure Cosmos DB was that it supported both SQL and graph query interfaces to support both requirements that we had for Datagroups. Another interesting aspect about Azure Cosmos DB is that the underlying data is stored in JSON format. However, it allows the data to evolve in a graph data structure, which really helps in the scenario where you start with a data in a document format, but eventually you can establish relationship between them. The Graph API for Azure Cosmos DB is powered by Apache Gremlin, which is an open source project. Being open source, there is a strong community that supports the query language and all of the knowledge behind this. As a result, we can rely on it to address all of our query needs. Another important aspect about Azure Cosmos DB was that its cost is associated with throughput and not the capacity. As a result, when we are building the service, when we are prototyping, testing, and when we don't have any customers onboarded, we can provision with the lowest amount of request units. And as we onboard customers, we can progressively increase this value. The most important aspect, which was really critical for us, was that it supports stored procedure to support transaction. And you can use stored procedure to update multiple documents at once, and that operation is atomic. This is how we use these features to build data groups. The CRUD and list APIs that we were supposed to build, we used Azure Cosmos DB's NoSQL API for consistency, since this API provides a query language that is more suited for searching and sorting operations. If you recall the scenario of dataset delete, where a delete of a single dataset requires atomic update on multiple data groups, we use stored procedure to perform that operation. So whenever a dataset will get deleted, we'll use stored procedure to update all of the data groups referring to this deleted dataset. The Azure Cosmos DB for Apache Gremlin was very helpful in simplifying how we fetch the most immediate ancestors and descendants for a given data group. As you recall, this was one of the requirements that for each read operation, we should return most immediate parent and children for a given data group. If you look at the query below, g.v.both.e, this query is basically doing just that. What this really means is that you provide the vertex ID or the data group ID in the v function, and it will return all of the edges for the given vertex, both inbound and outbound, which results in all of the children and parent to be returned for that given vertex. Now, in a traditional SQL syntax, this will be a complex operation, either performed by executing multiple queries or by creating a complicated query by performing a union or a join operation. However, Apache Gremlin makes it very easy. Now, at the start, I talked about how guardrails was very critical for us to achieve highest level of user experience as well as guarantee our query performance. We wanted to restrict the depth of the hierarchy that a user can have, as well as the number of children that a data group can have. Now, because we didn't want a scenario where a user is navigating through a data group and they are caught in an endless loop while navigating through data groups, as it has a very high depth, or their screen just freezes because they have a large number of data groups as its children. So it was very important for us to implement those guardrails, and Apache Gremlin was very helpful in implementing those guardrails. We use that query language to ensure such restrictions by parsing through the graph that we are storing. The last but not the least aspect of the Azure Cosmos DB that was very helpful was its cost modeling. As I mentioned earlier, during provisioning, we went with the lowest provision RU while prototyping and testing and building out our service when we didn't have any customer onboarded. And as we onboarded more and more customers, we progressively increased this value. So our cost model reflected the actual usage and not the provision capacity. All of these features really helped us build a service successfully that has scaled horizontally and has been a critical component within AEP. With that, we conclude this presentation, and I would really like to thank you for your time. My social media reference will be shared with you. Please keep in touch. Reach out to me if you have any questions. Once again, thanks and have a good day. Bye-bye.